So for the organic station, we just did several of the common organic tests with the view that you could see the positive results for them. There are two ways I could have done this. I could have done it this way, where you see the results of the test when it's positive, or I could have given you some unknown compounds and then had you do these tests to determine what the functional groups were. I thought at this stage more valuable for you to see what a positive result was. So we started off with what I'm calling the potassium dichromate test. This is acidified potassium dichromate. You could have used acidified potassium chromate because the active species in there is often called H2CrO4 or chromic acid. Either way, we've got chromium 6 in an acidic environment. Looks like this, a nice orange color, and a positive result is one in which that orange turns to green. Now you see this, as far as we're concerned with organic chemistry, with alcohols or with aldehydes, and the particular one you did was formaldehyde, otherwise known as methanal. And what happened to the methanal was it was oxidized to give you methanoic acid because the chromium goes from chromium 6 to chromium 3 in a reduction. Okay, there's some debate in the literature what we're actually seeing there. It's probably a mixture of chromium 3 and chromium 4, but the A-level board says it's green, it's chromium 3, so therefore that's what you need to know. Next one is one that is again debated whether to put it on there because a lot of A-level boards don't seem to notice this, but it is important that you see it, and this is dilute potassium permanganate. Take some of, in this case, the hexene solution or propantuol. So we're testing this on 2 species so you can see it. 5 drops of potassium permanganate, shake vigorously. Starts off being nice and purple, and it ends up with this brown precipitate. Okay, now this works for alcohols, it works for aldehydes, it also works for alkenes. The alkene reaction is possibly the one that you're not familiar with. This is where we take an alkene and we add OH across the double bond, so we make a diol. Now you should note that if we were to do this in a more vigorous fashion, we'd actually cleave the double bond, but again, I've only seen that as introduced in a question rather than being something you have to learn. But anyway, permanganate under these conditions, still relatively strong oxidizing conditions, but not hugely oxidizing. Double bond goes to a diol. The other thing you could have done was propantuol, a secondary alcohol, goes to the ketone, because what's happening here is that the organic species is being oxidized because permanganate is being reduced. The manganese 7 is going down to manganese 4. Now, permanganate is an amazing species. It's a wonderful oxidizing agent, but it can also confuse people because you're starting off with manganese 7, and depending upon what you do, you can go to manganese 6, manganese 4, as is the case here, or if you do it in acidic solution, manganese 2. Now this is another reaction, or probably the reaction of permanganate that you need to know. Permanganate in acidic solution from manganese 7 to manganese 2. This is a very oxidizing solution here, very, very strong conditions. But anyway, the test, the organic test, should it come up, is where you go from purple to the brown precipitate. Again, it is a indication that your organic group is something that can be oxidized. Bromine water is one that you absolutely do have on the A levels for something to do with alkenes. Bromine water looks like this to start with. You've finished, you've gone from the yellow-brown solution to colorless, and this works for alkenes, of course, but also do note for phenols, right? And I'll come back to that in a second. The alkene reaction is one that you study the bromination of the double bond, putting a bromine on each side of it. If you remember though, phenols, typically aromatics, if you want to brominate them, you have to use bromine itself and a catalyst, FeBr3, AlBr3, and so on. Phenols, however, so much more reactive that one of the tests for phenols, certainly one of the indicative reactions you need to know for phenols, is they don't need the very strong concentrated bromine or pure bromine with the catalyst. It can be done with bromine water. Iodoform one that will almost certainly come up on your test. Take what we're reacting up with, and we're using acetone, otherwise known as propanone by you guys. Everyone else in the world calls it acetone. You add in sodium hydroxide and then iodine till you see a result. And the result that you see is this yellow precipitate. Now, of course, you get a positive iodoform test when you have a methyl group on a carbon as an oxygen. The classic one is, of course, a double bonded O, but it does work if it's a alcohol group for it. So, of course, secondary alcohols in which the alcohol is on the 2 carbon, or ethanol are the alcohols that it works for. And then, of course, methyl ketones. The reaction that we're having in this particular case, there's the acetone, the propanone, there's the methyl group, we'll call it this methyl group next to a carbon oxygen double bond. And what happens is that you get an oxidation of the carbon containing compound going to the acid here, breaking off that rogue methyl group, which then has 3 iodides on it, I should say, as the iodine gets reduced. Sodium carbonate, very classic test, taking acetic acid, which of course you and nobody else in the world calls ethanoic acid. We add in some sodium carbonate solution, and what we see is a rotation of my video. So you see bubbles of it. I hate it when this thing does it. And those bubbles are, of course, of carbon dioxide. If we'd wanted to, we could have collected that gas and tested for it by putting it into lime water, which would have gotten cloudy. And this is the classic test for carboxylic acids. There's the acid, you react it up with sodium carbonate, and you make H2CO3, so-called carbonic acid, extremely unstable, immediately decomposes to give you water and the CO2 gas, which is what you see bubbling off. Do take note, of course, that carboxylic acids are not the only acids that do this. The standard mineral acids, that's your inorganic acids, hydrochloric and so on, will quite happily bubble away when you introduce sodium carbonate for them. So you should be absolutely sure that before you do this test that you have taken care of any other acid that might have been there in the preparation. But anyway, classic test for carboxylic acid bubbles when you add sodium carbonate or sodium hydrogen carbonate. FeCl3 test is where you take a few drops of the yellow FeCl3 solution, drop it into solution that contains a phenol group, and the colorless solution, usually colors, turns this lovely purple color. What's actually happening there now, the phenol that we took was salicylic acid, which is of course the precursor for aspirin, and you can see you got this phenol group there. The oxygen of the phenol coordinates to the iron to depending upon how much you like drawing hexagons, you can draw this with 2 hexagons or 2 phenol groups, 3 phenol groups as I've done here, all the way up to 6 phenol groups. Given how we've got the acid group floating around there on the number 2 carbon, highly unlikely we'd squeeze 6 of these around the iron, but the most important thing is you are making this purple coordination compound. And of course, you know, it's the transition metal center here, iron, so we expect to see a colored complex. Tollens test. Most complicated one really to do. You need to make up 2 solutions, feeding solution A, which is essentially copper sulfate, and solutions B, which is this sodium potassium tartrate and sodium hydroxide, placed in a water bath, leave a few minutes. Initially it's got this lovely blue of the copper 2+, and it turns to this red precipitate. Okay, now this works with aldehydes and so-called reducing sugars because it is an oxidation. Okay, and if it's an oxidation, something else is reduced, and what is reduced is the copper. The copper goes from 2+ to copper 1+, which is this red precipitate. Okay, what happens to the organic-y, especially as I use glucose here, too confusing to really put in here. The mechanism rather interesting with this tartrate anion in there that's supposed to bind the copper and protect it to an extent, so it just doesn't easily go from the 2+ to the 1+. Question that came up from a very well-thinking student during the test is, if this is copper 1, we're taught that copper 1 has colorless complexes, and indeed you expect copper 1 to have colorless complexes because the electron configuration of copper 1, just copper plus, is D10. And of course the way that most transition metal complexes are colored is because you've got a space to elevate a d electron from a lower d orbital to an upper d orbital. but of course there's no space for that elevation when you've got a D10 electron configuration. Now the reason I said most transition metal complexes are coloured is because in some cases the colour comes not from that mechanism, the elevation of a d electron from a lower d orbital to an upper d orbital, but some other mechanism. And in this particular case here, what happens is that you get an electron goes from the ligand to the metal when you've got just the right amount of light popping in there. That's what's known as a ligand to metal charge transfer complex, and that's why we get in the colour. The colour in this case nothing to do with the d orbitals on the copper, it has more to do with the electrons on the oxygen anion, the oxide anion, going into a vacant orbital on the copper. Finally, the Tollens test. This is the longest method. Clean a test tube with 3 molar sodium hydroxide, put in a little bit of silver nitrate, turns brown and cloudy, add ammonia until all that brown precipitate is dissolved, and then you add in, this case we're using methanol, right, otherwise known as formaldehyde, and the product you get, or the result you get, is this glorious silver mirror. Now much more often you'll get a black colour in there, or the silver colour sort of floating around in the solution. It took quite a while and patience to get this lovely silver coating around the test tube there, and that is of course a lovely test for aldehydes. And as with several other of these tests, it is a redox reaction. Here is our formaldehyde, or the methanol, oxidized to methanoic acid. If it's been oxidized, something else is being reduced, and what's being reduced is the silver plus that you start with silver nitrate, which ultimately ends up as silver solid, and that is of course that silver metal that is coating the test tube. I put in the intermediate reactions here. Silver plus goes to silver oxide or hydroxide. That's the brownish color that you get when you add the sodium hydroxide to it. Add in ammonia and it dissolves, and you make this diammonia, or diamine as it's properly called, silver 1 complex. This is the same complex that is formed when you do the silver halide tests. You might remember that a test for silver chloride is you add dilute ammonia and it dissolves to make this complex. A test for silver bromide is you add concentrated ammonia, and again the silver bromide precipitate dissolves because you're making this complex here, and doesn't work for the silver iodide precipitates. Anyway, see how all of chemistry ties together. Hope you enjoyed this particular set of experiments, and good luck on your exams.